Simplify radical expressions. We're about to start simplifying some more complex radicals, and the thing I really want you to do is to focus on one thing at a time when simplifying radicals. Simplify the coefficient first, and then do each variable separately, and it'll just make your life a lot easier. If you try to do them all at once, you're bound to make mistakes. So I want to go through this example. So we now have a mix of numbers and variables, and we started this earlier, but let's simplify this radical 72 n to the power of 7. So our strategy is going to be to look for the largest perfect square that's in each 72 and n to the 7, but we're going to start with the coefficient. What's the largest perfect square in 72? And if you want, you can just try dividing by stuff. You can do 72 divided by 9. So 72 divided by 9 is 8. And so that's one option. I could write 72 as 9 times 8, because 9 is a perfect square. However, 8 also has a perfect square in it of 4. So this isn't the largest perfect square we could pull out. I could try 72 divided by 16, but that's 4.5, so that doesn't work. So let's do 72 divided by 36. And if I do 72 divided by 36, I'm left with 2. So 72 is the same as 36 times 2. So here is my largest perfect square that's in 72 that I'm going to be able to pull out of this radical. Now let's carry on with the variable part. When I'm looking at n to the 7, I'm thinking about what is the what can I pull out of the square root from n to the 7? So again, I'm thinking about the largest perfect square. And for a square root, that's going to be the largest even power. So n to the 6 times n to the 1, the largest even power that's there, which is n to the 6, and I have 1 left over n, I can rewrite n to the 6 as n cubed squared. And the reason why I'm looking for that even number is because when dealing with square roots, anything times 2 is going to be an even number. So n to the 7, I'm looking for splitting off the largest even number, which is 6, and whatever's left over. And so I'm going to split that n to the 7 apart as n to the 6 and n to the 1, and I won't write the 1. And now I can pull out the n to the 6. And you've probably started to get the pattern that when you're pulling n to the 6 out of the square root, what you're essentially doing is dividing the power by 2. But you can see this by rewriting. So I'll write 36 times 2. I'll write this as n cubed to the power of 2. And then you can really see where that division of 2 comes from. And so now I have the square root of 36, which is 6 squared, and n cubed, also squared, and I have left over 2 times n inside the radical. Those are the guys that I just could not pull out, 2 and n, because there was no perfect square part of them. So left over here is 6n cubed square root 2n. That's my simplified expression. And now we're just going to start working through examples. So again, I'm looking for, in this question, I'm looking for perfect cubes that are inside of 24. So 24 can be written as 8 times 3. 8 is a perfect cube, and that'll leave me with 3, which has no perfect cube inside of it, so that's perfect. I've got my coefficient part done. 8 times 3. And how about 8x to the power of 8? So like when we were dealing with the even numbers, basically because I have a perfect cube, I'm looking for in the exponent 8, how can I write this with the largest multiple of 3? And so I could write this as x to the power of 6, because 6 is a multiple of 3, times x to the power of 2, because that will allow me to do x squared to the power of 3 in place of x to the power of 6. And this power of 3 is what's going to cancel with my cubed root. So I'll write this x to the power of 8 as x to the power of 6 times x squared. So this is the same as cubed root of, and now 8 is the same as 2 cubed, and x to the power of 6 is x squared. All of that part is cubed, so that's dealing with this and this. And then I also have the cubed root of the leftover stuff, which is 3x squared. So 2x squared times the cubed root of 3x squared. What perfect square is in 63? It must have 9 in there, so yeah, check it in my calculator. Actually, I should know this one from my times tables. 9 times 7 is 63, so we'll start there. And then u cubed, well, that would be u squared times u. So there's my perfect square there that will be, so 9 is a perfect square that will be pulled out, u squared is a perfect square that will be pulled out, and v I'll write as v to the power of 4 times v, because v to the power of 4 is also a perfect square. V to the power of 4, of course, would be v squared squared. So this is the square root of 9 u squared. I'll group all my perfect squares together. And so you can do this as you start to get comfortable with this, you can do this in fewer steps. And there's my leftovers that don't have any perfect squares in them. You can do this in fewer steps. And if you're comfortable, you can just take the square root of each thing. So I'll do that now. So square root of 9 is 3, square root of u squared is u, and the square root of v to the power of 4 is v squared. And then left over is 7uv. Here I have a fourth root. So this is where I'm going to need my calculator's help. What's the largest perfect fourth in 48? Well, I need to know some powers of 4. So, I could try 2 to the power of 4 to start. And I get 16. And so 48 can be divided by 16. And 48 divided by 16 is 3. So how about that? I use 16 times 3 for 48, because I know that 16 is equal to 2 to the power of 4. So that's what I'm doing there. X to the power of 4, well, I don't have to do anything about that, because that's already obviously a perfect fourth. And then y to the power of 7, well, I have y to the power of 4. There's a perfect fourth, and I would be left with y to the power of 3. So that's how I'll split apart y to the 7. So now grouping my perfect fourths, so that would be 16 and x to the 4 and y to the 4. And leaving me with the fourth root of 3y cubed. And now this would be 2xy with taking the fourth root of each of those items, and fourth root of 3y cubed. So it's just really important to be careful. Watch out for that index in the radical. If it's not a square and it's not a cubed, you might need to use your calculator for a little help. And one last example with a negative sign in there. So we have the cubed root of 27. Now the cubed root of 27 is already something that I can take the cubed root of. So I don't need to touch negative 27. A, there's nothing I can do about A. It's doesn't have any exponent, so I'm not going to be able to write that as a cube of something. And b to the 16. So b to the 16 is an interesting one. I'll do my work on the side here. So b to the 16, I need to write this as some multiple of b to the power of some multiple of 3 times the leftover. So what's the highest multiple of 3 is probably 15, and b to the 1. So if I use 15, I could write that as b to the 5 to the power of 3 times b, and that third power will cancel with my third root. So that's the way I'll go. So this is times b to the 15 times b, which means I have the cubed root of negative 27 is negative 3 cubed, and b to the power of 5 is, or 15 is, b to the power of 15 is b to the power of 5 cubed. So I can take the cubed root of those guys. And then I will have left over the cubed root of ab. So this would be negative 3 b to the power of 5 times the cubed root. Be very careful here. Make sure your index is very clear. Like I don't want to write it too close to the exponent b to the 5. I want to make sure it's really clear that that 3 belongs to the index of the radical. So just make sure you're very clear with your exponents and your indices, and you're writing them in the correct positions.